So we finished up our initial discussion, creating a model to describe our initial reaction. We can use that model to describe this reaction or our two dissolving reactions. Quite simply, what we now understand is that within each of these reactions, there's some exchange of energy. In this first one, we have more heat on the left side. So when this reaction occurs, we get colder. Same thing when we dissolve the ammonium nitrate. We had more heat on the left side. But when we dissolved the potassium hydroxide, we got more heat on the right side. And the outcome of the reaction, our solution was hotter than when we started. We were able to see that. We can now explain why these things could happen. But why don't we see more of these things happen? Why don't we see more reactions that get colder? In fact, why don't we see this process in everyday life? Why is it that the reaction can go this way, but it doesn't go that way? I mean, when I mix barium hydroxide and ammonium chloride, I'm removing heat and I'm getting all of these chemicals. But all of the same chemicals I started with, they're all still there. My energy didn't go anywhere, I actually absorbed energy. Why can't I release energy and go back to this? There's actually a lot of processes in our regular life that kind of work this same way, where they only go in one direction. Why can't they go in the other direction? I mean, if you think about it, we use a lot of energy in a refrigerator in order to keep our food cold. But what if the temperature, what if the refrigerator shut off? Well, the temperature would go back up. Our food would come up to room temperature. Why is that? Why wouldn't it stay cold? In fact, if I've got something like a cup full of ice, why is it that the ice melts? Why does the ice get warmer? Why doesn't the air around the ice get warmer and the ice get colder? Why doesn't the energy go in the other direction? What determines what direction energy flows? That's what we're going to be looking at next. We're going to try and answer those questions. And in order to do that, we're going to look at three specific processes. All right, so the three processes that we're going to look at are refrigeration, perspiration, and combustion. What we're going to try and figure out is which direction does the energy go and why, and where does it naturally want to go. So think about that in a refrigerator. If you put food into a refrigerator, what happens to it? Where does the energy go? Why would the energy go that way? Is that a natural process, or do we have to force that to happen? Another way to think about that is if I unplugged the refrigerator, what would happen? The next question is why. So we could say the energy leaves the refrigerator, but why? Could the energy go back into the refrigerator? Or if you think the energy is going into the refrigerator, could it come back out? Could this process reverse itself? If I unplug the refrigerator, could it do the same thing that it would do if it was plugged in? If I leave it plugged in, as long as it continues to get the energy it needs, is there a way that its process would just reverse on its own? Think about perspiration. What happens when I sweat? Why do I sweat? What's the purpose of sweat? Where is the energy going when I sweat? Think about combustion. Something as simple as candles burning. So we've got a couple candles right here. Let's light them, see what happens. So these candles are burning. What they're burning is the wax. The wax is a fuel source, just like gasoline in an engine or the natural gas lines in our lab. It's burning some kind of hydrocarbon, some mixture of carbon and hydrogen, mixing that with oxygen to produce carbon dioxide and water. Where is the heat? Which side of the reaction would I put the heat on? The other way to think about that is this getting colder or warmer? If it's getting colder, it's absorbing the heat, and there's more heat on this side. If it's getting colder, well then the heat's going to be on, or if it's getting hotter, the heat's going to be on this side. It's going to be releasing heat instead of absorbing it. So think about that. And while you're thinking about that, think about why can't it go the other direction? One last point to consider: if I have a glass of ice water sitting out in the hot summer sun, what's going to happen to that ice? So we've got that water, and then we've just got a big old ice cube in that water. What's going to happen to that ice cube? It's going to melt, obviously, we know that. So which direction is the energy going? Is the energy going into the ice cube, or is it leaving the ice cube? And why can't it go the other direction? Of course the ice melts, and the air around it, the water, gets colder. But why can't the water get warmer, and the ice get colder? Why can't energy flow in the other direction? So this one let's look at. Which direction is the energy flowing? Well, the energy is flowing into the ice cube. It's warmer outside and it's colder inside. So the energy is going to flow from the warm to the cold. So when we think about why can't the ice cube get colder and the water around it get warmer at the same time, that would mean energy is continuing to leave the ice cube. So what we're really saying is, why can't the temperature flow from cold to hot? So energy flows from hot to cold. The question I have is, why not the other way?